or scored to this computer. Okay, so now we want to transition to talk about compartmental models. Okay, I want to talk about equilibria and compartmental models. We've seen state space portraits like this, and we'll often plot them like this with an arrow showing the direction where they go in. And I've included some slides here that go into this a little bit more. But I want to talk about equilibria here. I want to get you positioned to take on some challenges with equilibria. So imagine that we have a model like this, right? Susceptible infective recover. This is a close cousin of what we're dealing with here. We elaborated it a little bit here. We embellished it with some logic for where we endogenized the mean duration of infectiousness, and that had big implications. And then we embellished it with some vaccination, but broadly it was it was initially just of this sort, right? And we could translate that, and in fact transliterate that into a set of differential equations. I think you know the rules for doing this, but I want to make sure people are equipped to do this. So I'm going to go back. This won't be needed for many of those in the class, but I want to make sure people are carried along. So when we have a model like this, right, this is a different model, we can transliterate this into a series of differential equations where inflows have positive signs associated with the rate of change of the stock into which they come, and outflows have negative signs, right? So we have a flow out from here to here. I'm not sure where, I think the head is hidden here. This is inflow, so it's with a plus. This is an outflow, so it's with a minus. And the same flow is a inflow to this stock. So it's comes with a plus into this one. So these two terms both reflect this flow. And then we have a minus for this one. And of course, this one flow contributes in a positive way for this particular model. So when you're dealing with a stock and flow model, you can transliterate it more or less directly into a series of differential equations. And frankly, it's, as is indicated with the duplication here, this isn't the most parsimonious way to express this model. The stock and flow model actually captures kind of a more parsimonious description, but you see the direct way which it can be translated into these differential equations. And I remind you that S dot means the rate of change of S over time, right? S dot being, if the time unit were days, what would an S dot equal to 5 mean? Someone fill in if we had a time unit of days, so T was measured in days, what would it mean if S dot is 5? What would that mean? Yeah, well, yeah, but S dot is 5. What about 5 people per day? It's S dot, it's not 5. It increases by 5 people a day. What if it were minus 5? What would it mean if S dot is minus 5? It decreases by 5 people a day. That's right. It's the rate of change. That's what the dot means, right? ds dt, the rate of change. How quickly it's changing compared to time, right? Per unit time, day, here, day. How quickly is it going up or down, right? Per unit time, it's rising by 5 per day, or falling by 5 per day, right? Same thing with I dot, how quickly I is changing with time, right? If I dot were 100, it would mean it's rising by 100 people per day. If I dot were 0, it would mean it's not changing at all per day. If I dot is minus 100, it'll be mean it's falling by people per day. I'm just trying to make sure people are brought along with this notation, so we don't, because we're going to be relying very heavily on it. Okay, so let's go back to our model of note here, and forgive me for jumping. I just wanted to bring people along for that. Here's our SIRS model. We can transliterate it into these formulas, right? Omega times R comes from this term. It flows in here, minus C times I over N times beta times S. Where does this term represent in this model? Where do I look? Where did this term come from in this model? Place it in the chat. Yeah, it's from infections. That's right. And so it flows out of susceptible, hence the minus, and into infective, etc. Yeah. Here we have mean duration of infections of tau, so that term appears here. It's an outflow from infectives and an inflow to recover. Okay. Hopefully you should be comfortable with the basic transliteration. Now, suppose we wanted to find the equilibria for this model. We need to, suppose we want to find the points at which it's in stasis, the points at which it's in balance. Remember when we saw that, when I say it's in balance, the model's in balance, I mean, all these stocks are not changing. I kind of put aside the cumulative number of infectives because technically that's a stock, but I didn't want it to distract you from things, just like I focused on SI and R for our little demonstration there. But what I'm talking about, when I say this system is in equilibrium, I mean S dot equals I dot equals R dot equals what? What does it mean for it to be in balance? That each and every one of those stocks is what? Is not changing. So their dot, S dot, I dot, R dot equals 0 for all of them. Remember, this equals 0, S dot equals 0 means it's not rising, it's not falling, it's staying the same, right? Its rate of change with time is 0. Yeah, that, right? It's not changing at all, right? Not changing at all. Same thing with I dot. Same thing with R dot. It's not changing at all. So when it's in balance, all of these values, S dot, I dot, R dot, they're all what? Put it one more time into the, yes, they're all 0. Please remember that. Please, for the final exam, don't say, oh, well, one of them is 0. No, they're all 0. All. Every stinking one of them. Every one of them. Okay? They're all 0. Okay. So suppose we know that they're all 0 for it to be in equilibrium. How would we find the locations of the equilibrium? What I mean by that is, please take note. What I mean by that is, what are the particular values for susceptible infective recovery, the particular locations in like a state space? What are the values of S, I, and R at which it's in balance, where it's not going to change anymore? It's neither going up or down. What are the particular values of S, I, and R for which it's in balance? If I posed you that question, what would you do to identify those points? The points, the value of susceptible, infected, and recovered. The points of states in state space, or the state in which it is in balance. Remember, in a dynamical system, the evolution of the system depends on the state, right? And we're going to find the location in the state, the value of the state, the particular assumptions about the state for which it doesn't evolve at all. It stays constant. It doesn't change at all. So what do I have to do? Okay, well, that's true. It'll be S dot equals I dot equals R dot, where they're all equal to what? You said it earlier. So Mark said S dot equals I dot equals R dot. Yeah, but they're all equal to what? When it's in balance, they're all equal to, you said it earlier. So, well, they're all equal to 0. Okay, so the question is, how do we identify the state at which that's true? How do we determine the situation as determined by the state in which it's true? What do? We have 3 equations, and what are we solving for? What are we solving for? We're solving for what? Yeah, we're solving for what? We're solving for SI and R. That's exactly right. I think that was Tusif who said it, or Tyler who said it. That's exactly right. Fiza said it. Karan said it. Rushil, all correct. Yeah, we're solving for SI and R for which it's in balance. So we're going to get out formulas for SI and R in terms of what? In other words, we're going to get a value for SI and R. S equals something on the right-hand side, I equals something on the right-hand side, R equals something on the right-hand side. What will be on the right-hand side? What sort of thing will be on the right-hand side? Well, no. No, if it were S dot equals thing, the right-hand side will be 0. I'm asking, we're solving for the state of the system, the situation for which this system will be balanced. We're solving for S, I, and R for which S dot, I dot, R dot are all 0. Yeah, well, you say the rest of the variables. But look, we want to find the values for S, I, and R for which the system will be in balance. We can't have, let's say, well, S equals I plus R divided by tau. No. I mean, we want to solve for their particular values. We can't have them depending on each other in this sort of way. So what's going to be on the right-hand side? We're going to solve for the values of S, I, and R for which will be in balance. Yeah, the form, okay, so be things in the equations other than S, I, and R. Yeah, that's exactly right. And what are those things in these equations other than S, I, and R? Yes, exactly, Rachel, exactly. Once again, Rachel hits it out of the ballpark. Omega, C, beta, and N. It's basically constants on the right-hand side. Now, of course, we could associate numbers with them, and we have particular numbers, but the things on the right-hand side, when we solve, so again, we're trying to find when the system is in balance. We're trying to find the situations for which the system is in balance, right? We're trying to we're trying to find the points, the situations where the system's not changing. What it means for the system to not change is that S dot, I dot, and R dot all equal 0, right? That's what it means for the system to not change, right? This is the system which is not changing. S dot, I dot, and in fact, the R dot all equal to 0. S dot is not changing. That's why it's not going along here. I dot is not changing. That's not why it's not going up or down here, right? And we saw this under, different particular circumstances, right? Like with 3/4 of the population vaccinated, in fact, never fully reached a situation with a balance, right? For healthcare workers here, 200, it reached a situation of balance with a low level of infection. You may remember, it's zeroed in. And in the center here, it's going to be in balance. Infective is not increasing. It's not going up or down. And susceptible is not increasing. So this is a situation that's in balance. S dot, I dot, R dot all equals 0. They're not changing. The state is not changing. That's what the dot means, right? It's not going up. It's not going down. It's equal to 0 is why it's in balance. So S dot, I dot, and R dot is 0 at this point. At this point. And what is the situation? What's the value of S, I, and R for which that is true, for which they're not changing? Well, we solve for S, I, and R values for them, which on the right-hand side are composed of constants and these values of parameters. Okay? Values of parameters on the right-hand side. Do you get that point? Because there's misunderstandings about this when I give it on quizzes or when I give it on assignments or when I give it on a final. Do you understand that idea? We're solving for, we're saying, where are these equilibria? Where are they located? Are they way the heck up here? Or they're way the heck here, or way the heck here? Where are they located? The values of S, I, and R at which it is in balance. That's what we are seeking here. In other words, where it's S dot, I dot, and R dot equals 0. So Jonathan asked a good question. Can we get it in equilibrium when we have a limit cycle? Yes. Well, that's why part of the reasons I asked earlier when we have a limit cycle, you recall that such a limit cycle came out when we had 3/4 of the population vaccinated here. Here we go. 3/4 of the population vaccinated. We went to a limit cycle, right? We never actually reached it, but I asked you, is there an equilibrium here? And if so, where is it? And you said, yes, it's in the center here. It never is reaching it because the logic of the situation conspires it from reaching it, just cycling around it in this stable way, this periodic way. But there is a point in here in which it's imbalanced, and you're absolutely right. It's somewhere in the center here that it's looping around. It yearns to be there, but it can never get there. It's like Sisyphus pushing the rock up the hill and rolling down on them, right? So there is an equilibrium. We could solve for it. And then actually, when you analyze any of these equilibrium, there's further techniques that are not very hard. It's basically the stuff you learned in linear algebra. You solve for the eigenvalues and eigenvectors around that equilibria, and you can determine, is it looping around it? Is it equilibrium that it's sucking things in and it approaches it? This is one where it's just looping around it. Guess what? The eigenvalues have imaginary components. That's why it's cycling, because e to the I pi is associated with a sinusoid. Or e to the I theta is associated with a sinusoid. E to the I theta t is associated with a sinusoid. And if you go to 90% people vaccinated, this is a situation where it definitely has a point of balance, and it's sucking things into that point of balance. We saw it earlier, okay, where it just sucks it down to this point of balance, and we saw that also with the baseline, right? It sucked it to a final point where it was in balance. It went through a bit of initial oscillation here, but then at a point in balance. So this is a point that just sucks it in. And with the eigenvectors, you figure out from what direction it sucks it in, how it sucks it in certain directions and in the state space. And when it's a spiral, it has a, so I characterized it crudely earlier. When it's a limit cycle, it can have a eigenvalues that are purely imaginary. So it's just in a cycle. It's not sucking it in, which would be negative real component. It's not pushing it out, which would be positive real component. But rather it's purely a cycle around it. Here, it's purely negative. There's no cycle going on here, and so it's around this. It's going to be purely negative eigenvalue. So it's just sucking it in like that. It doesn't always make that sound, although it's kind of cool when it does. And when you have the cycle around that we saw earlier, that it kind of loops around it and then comes into it, but it doesn't loop around forever. It just kind of approaches it here. This one is with a complex component. That's why it's looping around it right in that vicinity, but a negative. So it has some imaginary components, but a negative real component. So it's sucking it in as it's spiraling towards it. But that one where it just is a limit cycle, it doesn't suck it in. It kind of goes around in the stable way, never reaches it. So anyway, the stability of these can all be determined right around that point. You do what's called linearize the system. Around that point, you take what's called the Jacobian matrix and you solve for its eigenvalues and eigenvectors. You basically say around that point, it's basically linear, which is a very good approximation. You solve and you find its stability and you can determine what sort of thing it is. But that was a bit for those people who are eager for a little bit more detail. But what I need you to all understand, everyone in the class to understand, is that when you have a system like this, we solve for its equilibria by solving for the situation that gives for those equilibria, under what conditions they come about. And the conditions are the values of S, that's along this, the values of I, and the values of R for which it is stable, for which S dot equals I dot equals R dot equals 0. You solve for the value of S, I, and R in terms of constants on the right-hand side. What are those constants? They're the values of the parameters. C, omega, beta, tau here, and N, the total population, for which S dot equals I dot equals R dot equals 0. Now, how you do this requires a bit of care. It's a bit of algebra. And I'm going to ask you to, for those in 394, to try this. So we have to solve for the values of S, I, and R, for which S dot equals 0, I dot equals 0, R dot equals 0. How are we going to do that? Well, we have those equations, and we got to solve them for S, I, and R. Okay, so we can recognize, oh, there's a conservation. People not in S and I are in R. So there's a linear dependence, as Mark just said. Exactly. There's a linear dependence. Look, R is just the rest of the population. It's N, the total population, minus S minus R. It's like N minus quantity S plus I, right? This is basically saying this R is the rest of the population, okay? Yeah, so we can do that. So all we have to do is really determine S and I, the values for S and I. We can determine the value for R. So all we really have to do is solve for these two equations. What are we solving for? We're solving for S and I, for which S dot and I dot are both 0. Okay, so we have this system. We got to solve for this when S dot equals 0 and I dot equals 0. We're solving for S and I. All we did was sort of substituted this in for R here, and we got this system, right? We took this, and we plugged it in for that, and the rest we'll have like this, and we're solving for S and I when these two things equal 0. Here we can find two cases. One case is when it mirrors what we were saying the other day. I'm watching the time here. One case here is when I equals 0. So we want, if I equals 0, I dot equals 0, if this thing equals 0, then I'm just putting this right here. I dot equals 0. How do we solve for S and I, for this in terms of S? Well, look, we recognize this whole thing is I times this thing, okay? Okay, so this thing is I times, this here minus N, right? We're just substituting, we're multiplying by tau on both sides, okay. And this yields two cases. One, where I equals 0, right? If I equals 0, this is automatically true. That's one case we have to deal with. That's a distinct equilibrium. I equals 0. That will make this particular equation 0. And then we'd have to solve for S. But if I is not equal to 0, then what can we do here? If I is not equal to 0, what can we do to this to simplify it? If we know I is not equal to 0, what can we do which will allow us to solve for S? Can anyone say? Yeah, what do we, that's exactly right, Mark. Darn right that's true. For some reason, I can't get rid of that thing. Okay. Yeah, so if I equals 0, we can divide both sides by I. We know it's not 0, right? And we get this thing equals, so this thing equals 0. And then, as Mark said, you just move the N to the right, and you could do that, and then you could solve for S. Right? You can solve for the value of S for which this is true. And then we can use the other equation to solve for the value of I. Since we know S, we could solve for, we can use this equation because we've been using this equation. Now we could use this equation to solve for the value of I, plugging in this value of S that we solved for here when we know I is not equal to 0. If I equals 0, then okay, we can solve for the value of S from this equation because we know S dot equals what? What do we know S dot has to equal? Why do I say we can solve for this? We know S dot equals what? 0. Yeah. So we solve for it, as Mark says. Exactly. Exactly. So we solve for the value of S. Okay, if you're saying I equals 0, great. We just have omega times n minus S minus this whole term goes away. Omega times n minus S equals 0. And guess what? And you know, I have it here. You can follow it through. We don't have if we have this, then basically S equals n. What is that saying? If I equals 0, and S equals n, what is that describing? A population that's entirely what? I know we have to finish up. Entirely susceptible. No one's infective. Yeah, so that's an equilibrium. It's kind of a trivial equilibrium, or kind of a extreme case, right? No one's infective, everyone's susceptible, but it is an equilibrium. The other one is when I is not equal to 0, we just solved. And I kind of walked you through the first part of it, but as Mark said, S equal or n equals this, so we could solve for S as n divided by this. Guess what this is? You recognize that? Do you recognize this thing in the denominator here for which the system is in balance? What is this thing? Please. Okay, yeah, you got to go. Yeah, it's R0. This is R0. Yeah. As we said earlier, the system's in balance when the fraction of people susceptible is n divided by this, okay? And we can then solve for I, where this is not the case, and we get I being this. Okay, well, we'll finish up a little bit about this next time, but I think I may give you a little challenge to try this yourself. Okay, you got to go to class, and I got to check on things downstairs. Bit of a whirlwind thing. Hope that's useful in terms of thinking about solving for equilibria and also learning about state space portraits. Both of these will be valuable for thinking about with our next topic of agent-based modeling. Thanks very much. And I remind you that I'll be holding office hours now. Thank you.